I want to do another corollary to theorem 1.7. It has kind of a Tower Law feeling to it, although it's not. It doesn't follow from the Tower Law directly. So let's get started here. This is a corollary 1.9, and so it goes like this. So if m over L and L over K are algebraic, then the extension m over k is algebraic. So, I mean, it has kind of Tower Law flavor, and in fact, and I don't even know if this is worth putting as part of the proof. I want to prove it in general. So maybe before the proof, so let's say like this. So note, if everything's finite here, so if the degree of m over L is finite and the degree of L over K is finite, then of course the degree of m over K is finite by the Tower Law. So m over K, finite, that's Tower Law. And so m over K is algebraic by, what theorem is that? 1.7. Right, so by 1.7. So in the case that we know these are, if everything's finite, right? If these are finite, then we know that this is finite, and so that forces this one to be algebraic. That was our original theorem. But so now let's actually do the proof in general, where we don't make any assumptions about finiteness in the proof. So for the general case, here we go. So let's just pick an arbitrary element. So let's let z be in M. If I want to show that this extension is algebraic, what that means is that I need to show that every element, right, an arbitrarily chosen element in M is algebraic over K in this case. So since M is equal to, this looks kind of silly here, but it's true, right? M is equal to L adjoin M. There exists, right? What does that mean? That means that Z can be obtained using a finite number of operations using elements from L and M. So there exists, say, alpha 1 up through alpha sub probably n, alpha n in M, such that Z is equal to, how do I want to say this? Instead of equal to, let's just say, we don't need all of M to form, or to find Z. Z will live in L adjoin alpha 1 up through alpha n. Now, let's see. Each of these alphas lives in M, and this extension M over L is algebraic, which tells us that each of those alpha i's is algebraic. So now, and I should say algebraic over L, so each alpha I is algebraic over L, and so what do we know? If we take let me finish the sentence here. And so L adjoin alpha 1 up through alpha n is algebraic. Actually, I can say this better. I can say this let me say this, the extension is algebraic. This is by corollary, is at 1.8, I think, right? So by corollary 1.8, which says if you start off with a field and adjoin a bunch of any collection of algebraic elements, right, then the resulting extension is algebraic. So that's corollary 1.8. Okay, so if it's algebraic, then this extension has finite degree. So by theorem 1.7, the degree of L adjoin alpha 1 up through alpha n over L is finite. Do I need to give it a number, or can I just say it's finite? Yeah, so it's like that. And so there exists some natural number k. That's a little k there. Let me use a different, since I'm using k somewhere else in the proof. Let's use t. So a natural number t, such that. So this right here has finite degree, which means that let's say if we call it t, so there exists t such that the set 1 z squared all the way up to z to the t, this is linearly dependent. So this is linearly here. T could just be equal to the degree of this extension, and then we're guaranteed, because we have t plus 1 elements here, that that's going to be a linearly dependent set. Okay, so what does that mean? Well, okay, so that means that there is some non-trivial linear combination of these that adds up to 0. So thus, there exists beta 1 up through beta, subscripts here. What do I use? No, you need to use t. And the coefficients, of course, are going to come from L. So these are in L, such that beta 1. Oops! I need to call that beta 0 there. Beta 0 plus beta 1 z plus plus beta t z to the t is equal to 0. And I need to say not all 0 here, where not all beta I equals 0, right? So it's a non-trivial linear combination that adds up to 0. Okay, fine. Now, we could view these betas right here. Yeah, they live in L, but we could view them as living in K adjoin beta 0 up through beta t. So let's say it this way. It follows that z is algebraic over a K adjoin. Oh, do I want to say that? Yeah, fine. We could have the coefficients. We're choosing the coefficients in L, but because they're all betas, we could choose them or think of them as living in K adjoin beta 0 up through beta t. And so, let me continue this sentence here. The extension K adjoin beta 0 up through beta t along with z over over, or the degree of this extension, now I'm just going to do betas here. That's finite. So now, now I'm going to do Tower law. If I look at the degree of the extension k adjoins z over k, and apply Tower law here, so this is going to be k, it's going to be this one, k adjoin beta 0 up through beta t. Is that what I want? No, yeah. Oh, with z, k adjoin beta 0 up through beta t, times, now I'm going to repeat myself here, k, wait, something's weird here. Oh, yeah, because I can't say it's equal. I can say it's less than or equal to. Oh, I'm sorry. I'm making typo. Sorry, I need to redo this line. I apologize. That sucks. Okay, so now, I'm blowing the punchline here. So now, if I look at the degree of k adjoins z over k, it's going to be less than or equal to k adjoin beta 0 up through beta t, along with z over k. Now I'm going to do, okay, so now, okay, let's see if this makes sense, right? So the degree of this, right, the dimension of this vector space could be smaller than the dimension of this vector space, both viewed over k. Now Tower law, so that's equal to k b0 up through bt, comma z, over k adjoins z, right? No? What? No? Okay. Right. Oh, yep. Sorry, I'm getting all fuzzy on the subscripts here. So k b0 up through bt times k b0 up through bt all by k. Yeah, there we go. Sorry. Now, we know that this one is finite. And why do we know that this one is finite? Right, I need to actually explain why that is. Okay, so since, okay, so new one. So since each beta I in L and L over K, or not, I don't need the brackets there, and the extension L over K is algebraic, you see that the extension, oh, right, K adjoin beta 0 up through beta t over K is algebraic by corollary. So this is once again by corollary 1.8. So what did we do? We took a bunch of elements that are algebraic over K, or yeah, over K, and adjoined them to K, right? And by corollary 1.8, when you adjoin a set of algebraic elements, it yields an algebraic extension. So now we know that the extension is finite, which tells us, or now that tells us that the degree is finite. So it follows that K B0 BT over K, that degree is finite. That would be by 1.7. So by theorem 1.7. So now what we know is that both factors on the right-hand side are finite, which means that this one is finite, which will tell us that Z is algebraic over K. So now, so it now follows that the degree of K adjoins Z over K is finite, and so Z is algebraic over K, and that's what we needed. Remember, we were trying to show that M over K is an algebraic extension, which means that we needed to show that every element of M was algebraic over K. We chose our arbitrary element Z. We showed that it's in M. We showed that it's algebraic over K. That completes the proof. Now, this next definition is going to seem really kind of, I don't know, out of left field. It just sort of, where did this come from? So, oh no, I don't want a theorem yet, I need a definition. So I just want to start off with an extension. So let's let L over K be an extension, and then here's the weird part that sort of unexpectedly shows up. So and let tau from L to L be a monomorphism. In the ring sense, right? And so, or field sense, if you like. So it is a one-to-one homomorphism from L to L. Now, if T of little k is equal to little k for all little k in capital K, then what we say is that tau fixes k. So then we say that tau fixes capital K. Right, that's the end of the definition. Another way to think of this, though, is that tau restricted to K equals the identity map. Okay, so where did this monomorphism business come from? Well, we'll see that this actually is extremely important. And in fact, so our next theorem here is going to be a result involving this concept here. So if L over K is algebraic, and we have a monomorphism that fixes K, so and tau from L to L is a monomorphism that fixes K, then tau is an automorphism. So it's a curious result. And so what this is saying is, if you have, as long as you got an algebraic extension, and you know that you have a monomorphism, right, then you get onto for free. So, it's true. Now let's prove it. How much time we got here? Right. All right, so all I need to do, the whole point here, we need to show that tau is onto. So I'm going to choose somebody in the codomain L, produce somebody in the domain that gives us that output. So let's just call it Z. So let's let Z be an element of L. And okay, so Z is algebraic over K, which means there's a minimal polynomial. And I want to look at the roots of those. So the set capital R of roots of the minimal polynomial m sub z is finite, right? If you have, I mean, a polynomial of degree n has at most n roots. And I want to write out the minimal polynomial now, so let's just so let's write m sub z equal to, well, it'll be like k0 plus k1x plus k2x squared plus dot 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 k sub n, probably. Yeah, k sub n x to the n. K sub n x to the n. Now, I want to take a root of this polynomial. We know that z is a root, right? Let's just take another root. So given alpha in R, observe that. Now what I'm going to do is I'm going to apply tau to alpha, and then I'm going to plug the result into m sub z, right? So I want to look at, observe that m sub z of tau of alpha, and let's just crank this out. So that's going to be, well, it's going to be k0 plus k1 tau alpha plus k2 times tau of alpha squared plus blah, 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 plus k sub n. Tau of alpha raised to the n. Fine. Oh, but what do we know? We know that tau fixes k. So each of these k sub i's here could be rewritten as tau of the k sub I. So this is equal to tau of k0 plus tau k1 times tau of alpha. And then you keep going, eventually you'll get to tau of kn, and then I can write this as tau of alpha to the n. I'm just using the fact that it's a homomorphism, I can bring that n inside. Oh, and then I want to use the fact that it's a homomorphism and join it all into the single piece. So this is tau of k0 plus k1 alpha plus dot 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 plus kn alpha to the n. That's equal to, oh, what is this? Well, this is tau of, so this is the result of plugging alpha into the minimal polynomial. So this is m sub z of alpha. Oh, but alpha is a root of that polynomial. So that means that this is 0 inside the parentheses. So we get tau of 0, which is 0. So what does that mean? It means that tau of alpha is a root of that polynomial, meaning that tau of alpha is an element of R. So it follows that tau of alpha is an element of R. In other words, and let me continue this. So tau permutes the roots of m sub z. That observation right there is one of the key observations of Galois. Somehow what he's doing, and remember, a permutation, that's a symmetry of the set. And so tau, somehow these automorphisms that fix k correspond to symmetries of the set of roots of the minimal polynomial. And when we say the word symmetry, now you can see where group theory might come into play. And that was really the genius of Galois, is somehow recognizing that the study of polynomials is connected to the study of symmetries of roots, which then involves group theory. So it provides this connection between group theory and the study of roots of polynomials. Of course, there was no such word as group there. He essentially invented group theory by doing or by recognizing this. But it's that sentence right there. If not that, that right there is in some sense the key, or at least one of the keys to Galois theory. Okay, so now since tau is 1-to-1, we have, okay, so let's see. That would mean that the restriction, so tau restricted to r, from r to r, is 1-to-1. And since r is finite, this is sort of a Math 248 thing. If you have a 1-to-1 mapping from a finite set to a finite set, if it's 1-to-1, then you get onto for free. So since r is finite, we have that tau restricted to r is onto. Okay, fine. If it's onto, remember we started off with z, so it follows. So if it's onto, and we have z living in here, then there's somebody in here, so that when you plug it into tau restricted to r, you get z. So thus, there exists some alpha in r, and by the way, R is a subset of L, such that tau of alpha is equal to z. Okay, technically it's tau restricted to R, but so what? Alpha lives in R, so this is true. Therefore, tau is onto. And that's what we needed to complete the proof. Now what we have is if you have a monomorphism that fixes k, then it has to be an automorphism. So you get the 1-to-1-ness for free. That's the end of this chapter. Let me just say a little bit. I'm not going to prove anything more, but let me just open the new chapter and get it going for just a little bit. And I'm looking at my phone here. I can see that it's just about out of memory. It's telling me how much time I have left on my... I don't have a whole lot more left. I'm going to have to delete. I haven't deleted my videos for a while. So, so let me get this started, and I won't go for too much longer, so just deal with it. Okay, so this is chapter... Oh, no, it's not. It's chapter 2. It used to be, in my notes, it used to be chapter 3. So let me fix that real quick. I'm renumbering things as I go. Okay, so chapter 2. And the title of chapter 2 is Splitting Fields. And so we'll start off with a definition. So let's let's just start off with an extension. It doesn't have to be algebraic. So let's let L over K be an extension. and we need a polynomial, and let f in k bracket x, so just some polynomial. Then f splits over L if there exists, let's say, C in K and alpha 1 up through alpha n in L, such that f is equal to c times x minus alpha 1, x minus alpha 2, dot, 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 x minus alpha n. So if you can factor your polynomial completely into degree 1 factors, here I've written them as monic, so pull out all the, I'm going to say, pull the leading coefficient off of f, that's your c, and then factor the rest of the stuff so that you get x's here in the front, right? And so it's basically pull a unit out to make it so that you can multiply it by monic or write it as product of monic ones. Okay, so that's what it means to split over L if you can factor it as constant times degree 1 polynomials where the degree 1 polynomials live in L bracket x. So for example, if f equals x squared minus 2, think of this as a polynomial in Q bracket x, then it certainly splits over R, so this splits over R. The next polynomial, let's call it G, x squared plus 2. Now this does not split over R, right? Thinking of this still as in Q bracket x. It doesn't split over R, but it does split. So this splits over C, right? Because it's got imaginary roots. And here's a sort of key observation also. I don't know how key it is, but let's just note that f also splits over Q adjoin root 2. And somehow we want to think of this is better, right? That we don't need all of R. R is uncountable, right? We can be a bit more efficient, right? F splits, we're thinking of it as a polynomial with rational coefficients. It splits in the field that we obtain by just taking the coefficients and adjoining one of the roots. Really, we join both plus or minus 2. So we throw plus or minus 2 in there. That's all we need. We don't need all of R. And so that's nice. It's somehow a more efficient extension to work in. So now a definition. In fact, we'll leave it with this. So an extension L over K is a splitting field extension where'd it go? For F over K. So it's kind of a mouthful there, splitting field extension for F over K, if two things happen. So if the first one, the polynomial F, which we're viewing as K, in K bracket X, splits over L, fine. But we want it to be the smallest. We want L to be the smallest field, smallest extension over which F splits. And so it would go like this. So if say L prime contains K, so lives intermediate, right, to K and L, contains K, is contained by L, and F splits over L prime, then L prime has to equal L, right? So there's nobody strictly smaller than L over which F splits. Okay, so that's the definition, and maybe just one. So I usually will shorthand this and not say the word splitting field extension. So typically, what we'll say, let's say shorthand is L over K is a, and in fact, usually I won't even write the extension part. I'll just say L is a splitting field for F over a splitting field for F over K. Okay, so that's a good place to stop. We'll pick up and start getting results about splitting fields the next time.